My name is Stephanie Holshoe, and today I will be discussing constraining West Antarctic snow variability with GNSS Reflectometry. My advisor for this project is Dr. Matthew Siegfried, and this is for the Department of Geophysics. Antarctica is one of two polar ice caps on Earth, where 98% of the continent is comprised of the Antarctic ice sheet. In recent years, there has been much discussion about the impact of ice sheet melt on rising sea levels as a result of global climate change. To understand this melt, surface mass balance is often studied. Surface mass balance represents the relationship of loss and gain, in this case, loss and gain of ice sheet mass. It is approximately equal to gain, i.e. snowfall from precipitation, minus loss, i.e. runoff or evaporation. It can be a positive or negative value depending on the magnitude of these values for gain and loss. However, the loss is happening at rapid rates. Here the diagram shows from observational change and ice mass the loss that is occurring over time in Antarctica. Loss is shown quickly in red and orange colors, and it is happening most severely on the coast, mostly on the western coast. The gain occurs from snow accumulation, and it is shown in blue colors. The area of focus for this study will be on the western coast, since this is where the melt seems to be occurring the heaviest. So we know that surface mass balance is changing, but by how much? Unfortunately, that can be difficult to answer. Models that predict ice sheet behavior are being complicated by a few things. First, there are a lack of observations that would act to verify and constrain the parameters needed in physical and atmospheric models for ice sheets. Antarctica is approximately the size of the United States and Mexico combined, with only 118 observation stations located throughout its continent. This is like predicting the weather in the United States and Mexico using only 118 weather stations. It would not be very representative at all. Secondly, ice sheet models are complicated by uncertainties and firn column compaction. Firn is the middle phase of snow accumulation between fresh snow and ice. Firn columns compact with the oldest ice on the bottom and the newest snowfall on top. The top can melt and turn to runoff, but it's hard to understand how much. Based on how the firn will compact, this will affect how much runoff will occur. This can lead to uncertainties when dealing with ice sheet models. There are also uncertainties in snow accumulation and how snow is distributed across ice sheets, which again affect these models. The research for this project focuses mainly on targeting and constraining the variability in snow accumulation as mentioned from the previous slide. In order to improve ice sheet model predictions, we use Global Navigation Satellite System Interferometric Reflectometry to quantify snow accumulation over time in various locations across West Antarctica. GNSS-IR, for short, was developed by Larson et al., and her GNSS-IR software was used in this project to process data collected. GNSS-IR is a method that modifies and takes advantage of traditional satellite technologies. Under traditional satellite use, signals from the GPS are transmitted and hit station receiver antennas. However, not all signals directly hit the receiver antenna. Some station signals will hit the ground first, then hit the receiver antenna. This is traditionally referred to as noise, and it is typically filtered out of satellite processing. GNSS-IR uses this noise in a different manner. Given that the indirect hits have a longer path, shown in red in the diagram, the indirect signal will interfere with the direct signal path, shown in blue in the diagram. The ratio and strength of this interference is recorded as a signal-to-noise ratio. Using some geometry and knowledge of the elevation angle, the height of the reflector can be found. Now, given that the original reflector height was recorded when the antenna was installed, any new recorded reflector heights can be compared to the original. As snowfall accumulates on the surface, the reflector height will decrease. Thus, now we can learn about snow accumulation over time as a function of reflector height. The GNSS stations that are used in this analysis come from 118 long-term existing stations positioned across the continent. As shown on the map to the left, there are subsets of stations located throughout the continent. The subsets that are focused on this analysis here are located in the bottom right corner. The right map shows the subset zoomed in. Here stations GZ01 through GZ05 are positioned in a linear pattern, as well as the stations GZ12 through GZ16. Here, GZ means grounding zone. These lines of stations were studied for this analysis in hopes of gaining information about how snow accumulation and distribution varies on a small spatial scale. Each GNSS station contains solar panels, batteries, and antenna receivers. The solar panels charge standard car batteries which power the antenna. However, since solar panels are daylight dependent and sunlight dependent, and thus will cause the car battery charge to be dependent on sunlight, the stations will turn off when they don't have enough power. Sometimes they turn off for many months during the wintertime. Other times, a sunny day will cause them to turn on for a few days before turning off again. As a result, the data that is collected can be left with gaps in the time series. The data is recorded throughout the day, leaving approximately 70 to 80 readings per day for the reflector height. These are filtered based off of constraints such as elevation angle and determining whether or not a station has collected an improper or proper reading. From this information of reflector heights, time series can be created. This time series is for the stations of GZ01 through GZ05 for the years 2011 through 2013. The solid line for each station represents the median reflector height, and the shaded region represents the accompanying 95% confidence interval for the median height. This represents the variability and the measurements that were recorded for reflector height. Here it is seen that reflector height decreases over time. A decrease in reflector height represents an increase in snow accumulation. This makes sense seasonally, since summer in the northern hemisphere is winter in the southern hemisphere. Thus, as shown in the graph, around July 2011, the reflector height is the lowest, meaning snow accumulation is the highest in the wintertime. As mentioned before, the gaps in the graph are due to the stations turning on and off, leaving unrecorded data. Overall, we can see that for the majority of the confidence bands around each of the median station reflector heights, each confidence band isn't very wide. This means that the variability is pretty low for what we are representing here. Thus, this method can be trusted to be measuring reflector height with low variability. This time series is for the stations GZ12 through GZ16 for the years 2012 through 2014. Again, a decrease in reflector height represents an increase in snow accumulation. What's interesting to note about this graph is it shows much less variability between stations compared to the previous graph. Here, stations GZ15 and GZ14, shown in green and blue respectively, almost overlap each other for the entire time series. This means that the reflector heights that were being recorded, and thus snow accumulation, for each of these sites didn't vary very much between each other. So the snow distribution between these were pretty consistent. It is clear that this method shows with low variability the snow accumulation that is occurring over time. For further research, cross-correlation could be performed to define and quantify how much snow accumulation is changing between stations. So in the previous example, GZ15 could be cross-correlated with GZ16 to quantify just how little variance they have. Additionally, wind analysis could be used to understand snow distribution across a linear setup of stations. This would allow an understanding of how snow is affected by wind distribution over time. Finally, some stations are being constructed and mounted on top of towers instead of being simply 1 to 2 meters tall. This increases the footprint that snow accumulation can be studied with and can be useful in understanding our readings better. Overall, we found that this method captures, with low variability, snow accumulation and compaction seasonally. These measurements can be used to improve the parameters of physical models and to validate existing models commonly used for ice sheet behavior. Furthermore, with better constraints on the behavior of surface mass balance of these ice sheets, ice level rise projections can be more accurately portrayed to scientists and global policymakers alike. Thank you for your time.